Okay, so I guess this talk's going to be a little bit of a talk about people who have had frustrations, and that's one of my primary reasons why I work on ZFS. I'm basically trying to solve problems that I'm encountering. Just a quick question. Raise your hand if you're running a ZFS pool of substantial size, let's say 50 terabytes. Okay, and which ones of you are running Scrub or Resilver regularly? Okay, about half the hands. And which ones of you enjoy the experience? You guys are crazy. Anyway, so we understand that the problem basically is that these operations, Scrub and Resilver, are take a really long time, and to many people, it would seem that they take a little bit too long to be in any way sensible. So I'm first going to do a quick design recap of people who are maybe not quite familiar with the object model and the general model of ZFS. And so as a quick overview, basically the way we can view ZFS at the object level is it's basically a flat database. There's the hierarchy itself of the file system is built up, as was previously discussed, using an upper layer ZPL, but the actual base structure of the file system is flat in itself, and it's based around the notion of constructs that we call objects, and the objects are, you can think of them as basically like a flat plain file. It's just an array of blocks with a number. It's identified by a number, and we sometimes group these things. We always group these things into things called object sets, and yeah, basically that's the way ZFS looks like at one of the lowest layers, and the thing that implements this layer is referred to as DMU. The key thing to note here is that DMU doesn't really care about the structure of the objects inside. All it knows is it only understands enough to be able to find all the objects and read their contents, but it doesn't really care whether there's any linkage between them or any kind of structure to them. It understands only how to get to the objects, how to get to all the parts of them, and how to check some and make sure that they are all consistent. So everything that you see in ZFS as a user is built as an object. Any plain file in the directory, any even symlinks and attributes on objects, zvols, everything is built out of these object nomenclature, out of these object things, each with a specific binary format inside, but basically that's what we're looking at. And so graphically, this is about what it looks like. It's a little bit of a simplified view, but you can view these things, these D nodes, as essentially your objects, and each of them has a specific data type, each of them has a specific piece of data and structure inside, and then we group these together into these things called object sets. So there. Actually, I'm going to use one more slide for that in order to describe what's going on. So these objects are, too many file system gurus, they know that the only sensible way to design really such a data structure is in kind of a tree-like thing with lots of indirection in between, and this allows us to not have like a fixed size of an object, or be able to like punch holes in it, have pieces of it that are missing, and things like our copy and write structure, so we are able to reallocate a file. It's not just, you don't have to have a file on disk as a contiguous thing. You can just move it around bits in there. And the only way to do that sensibly is to have it as a tree of indirect blocks that then refer further down, everything. And so these indirection levels in ZFS are numbered, and they're numbered from the bottom up. So at your lowest level 0 that's where actually the object's contents live. This is frequently referred to as user data, or the actual useful data of ZFS. And anything above that, that's higher than level 0, is your metadata. So that's the thing, how to locate the actual contents of the objects. And so the important part here is the disparity in amounts of data, and this little picture here does not really capture that all that well. You have to understand that the upper part, which is all the indirections and basically the levels of the tree that are not that don't contain your user data. The user data is down here, but the upper parts up there is just indirections into the lower level blocks. And you got to keep in mind that this is a tree that expands out very, very quickly. The upper layers there are really a fairly small amount of data volume. It's usually only about 1% or thereabouts. Most of your blocks on disk are going to be these very, very bottom level blocks. So that's where pretty much all of your space usage lives. And so the DMU is also the thing that implements the ability to scrub and resilver. And what they do, fundamentally, scrub and resilver do the same thing. It's the same algorithm, pretty much. All they do is they just go through all the objects, read all the blocks, and they just check the checksums. Scrub and resilver does not care about the structure inside. It doesn't know anything about directories. It doesn't know anything about symlinks or hard links or anything. So that's why some people who think that ZFS has a sort of a checksum in terms of, like, they'll tell you just run scrub, that'll check the file system. It really doesn't. Scrub only ever verifies that the stuff on disk checks out with the checksum. It doesn't care about link counts. It doesn't care about loops and directories. You can create all of that if you wanted to with the appropriate editing tools. And so resilver is just a variation of the idea of scrub in that if you have a broken drive, we will simply reconstruct the data on it. And so that's the basic idea behind these two things. Now, the important thing to note here is that these operations are performed in order on a given object. So if you have a file that consists of 2 terabytes of data in sequence, it'll just start at the start of the object and just pretty much work its way forward. And so the algorithm, to summarize it in a really quick way, is just grab an object, read through all of its logical blocks in sequence. And logical, I mean the way that the block is represented inside of the object. And then just grab the next one and repeat until you've passed over everything on the file system. Now, this is all very good if the file system, if the on-disk layout looks pretty much the same or runs approximately in sequence to how you have it in the object itself. So if we, so this is just another representation of roughly what it will look like in the tree sort of layout. So you would jump up to a very high level where you're where you're basically looking at the top level of indirection there, and then you recurse down, and once you reach the very bottom layer, you would basically issue a ZIO read that would get sent right away to the drives, and you keep on going. You just keep on following this tree structure until you've consumed everything in sequence in the object itself, issuing any I/O as you go. Now, this is all working all very well if you're on initial layout. So this is sort of 2 scenarios where you've just about initially written an object. So let's say that this object was written, it's got 7 blocks in it. You've written it in 2 sets, like blocks 1, 2, 3, and then at some point later you've written blocks 4, 5, and 6, and 7. And so usually what ZFS will do is it'll try within a reasonable amount of time, if you've written chunks at the same time, it'll try to write them in sequence. After some time has passed, maybe there's a little bit of data extras accumulated on the pool, and then you write out the subsequent portion. And so from the point of view of the resilver, what it'll see is it'll issue reads for blocks 1 through 7, pretty much in sequence. And the disk, what the disks will see is they'll see blocks 1, 2, 3, skip 4, 5, 6, and 7. So that works reasonably well. This is on your initial writing when you've just filled up your file system and you're going to be running scrub or resilver. Now the problem is, what happens if you've rewritten lots of data? If you've gone in, so your typical database use case, database comes in, modifies a block, goes away. Goes in again, modifies another block, goes away. And these things tend to basically spray out the physical layout of the file over the disk in pretty much random order. So now when you scrub, when you read the object in sequence, you'll end up seeing blocks 1, 2, 3, 4, 5, 6, 7. You'll issue all the reads in sequence. But what the disk will actually see is it'll see, okay, I got to read block 1, then it'll do a seek, block 2, seek, and so on and so forth. And Paul is just currently checking the layout there. It's completely... But yeah, pretty much it'll just jump around. A little bit of, yeah, disks are able to a certain degree, reorder reads, but this will basically, if you have a large enough object, it will overpower the ability of a disk to reorder anything. And you'll end up converting your initially, you'll think that you're doing sequential reads on the object, but because of all this rewriting, what you'll end up hitting the drive as is random reads. Now, that's obviously a little bit of a problem for performance. So the improvement here is obviously to try and not do that. So basically the question is, how do we get I/O back into order? And the way we've done it is we split up this scrub and or resilver into two sections. We first, essentially, we scan as much of the data set. Now, these things are they're not sequential. They're pretty much operating in parallel. But we split up the process into two sections. We first scan through and try and discover as much of the end user data, which, remember, is 99% of your data. We try and discover as much of the locations of the blocks on disk. Then we do something to them, and then we set them off to be read or resilvered or anything. So in order to do that, we have introduced a per top-level VDEV reordering queue, because when you're scrubbing or resilvering, you really don't care in what sequence the blocks are being rebuilt, as long as it's all done by the end. So we just reorder everything, and the IOs that have been generated during the scanning phase will get queued up, reordered, aggregated, so that we know which ones are close together, which ones aren't, and then we'll issue it in a relatively sensible sequence. So this is pretty much how it looks like after we introduce our changes here for the improvements. You come in from the top. Again, the algorithm for scanning is unchanged. So from the point of view of the code base, it's really not that much of a change. What has changed is that once you reach the level zero blocks, we don't then try to issue ZIOs right away. We sort of record them somewhere. And the queue then, I'll be talking in a little while about the queue, how it works. But the queue takes care of making sure that stuff is as much in disk order as we sensibly can make it. And then at some later point, it'll start to issue the IOs seemingly out of sequence from the point of view of the file system, but they will actually be in sequence from the point of view of the drives. And when I'm talking about caching ZIOs here, we're not actually caching the full ZIOT structure. We're just caching just enough information in order to be able to construct the ZIO, because the ZIOT has a lot of information in it that we don't really care about. So this is the kind of view that we have from a system topology point of view. We have a top-level VDEV, and each top-level VDEV gets its own queue, because each top-level VDEV is pretty much the thing that matters about disk layout. So we track it per top-level VDEV and then reorder for it for the particular disk sequence. So how are the queues implemented? The queues primarily keep track of two things. They keep track of the individual reads to be issued, so the ZIOs, although as I said, it's not the actual ZIOT structure. And the reason why we keep that around is because the ZIOs contain the block pointers, or they tell us about the block pointers, and the block pointers tell us the checksums of the data that we got to check. The extents are the second kind of thing that we track, and extents are, from the point of view of this set of changes, from the point of view of improved Resilver, is just a loose collection, or well, it can be actually a fairly tight collection, but it's a collection of reads that are close together and in sequence, so that we know that they sort of represent a good target of opportunity where it could go in and issue a lot of I/O in good sequence. And the sorting queue itself consists of principally 3 trees, pretty much, and they all sort of interact with each other. We have a tree that tracks each extent sorted by the aggregate size of the constituent ZIOs, so we know how large an extent is and how much of it is actually filled with ZIOs, so we know roughly how valuable it is. And at the front of the tree, we have sort of the biggest, chunkiest targets that we might want to work with. Then we keep, obviously, extents tracked by address on disk, so we know how to assign ZIOs to them as they come in. And the ZI, then, of course, we keep track of the individual ZIOs that are to be issued. So this is sort of the layout, roughly what it looks like. From top to bottom, be extents by size, by address, and then finally the ZIOs by address. And as you can see a little bit over here, we can see that one of the extents, we call them scanning segments, they don't have to be necessarily completely filled with ZIOs. We do allow for a little bit of inter-ZIO gap because drives are pretty efficient at skipping that. But if the gaps are too large, we just consider that to be a separate ZIO, separate extent. And so obviously we aggregate those into these larger extent structures, and then we sort them by size so that we know which ones are the juiciest ones. And the algorithm for that is a little bit more complicated than just we sort by size. We actually also do consider how well filled they are. So for example, this guy over here, even though he's fairly large, he has a few chunks missing in it, so we do weight that a little bit in the algorithm, so that we know that, for example, somebody who's a couple of bytes shorter but completely filled up, we do consider that one to be more valuable than the ones that are like full of holes. So say say for instance we get a new ZIO that comes in. So over here we got a new ZIO being about to that was requested to be queued. You can see that it bridges the gap between two extents. So obviously then we gotta reconstruct the extents. We'll join these two together. And then, of course, this is a new large extent, so it'll get put up into the front of the queue, and it becomes our primary, sort of most valuable target. Now, this is all talking about how to sort the I/O. Now, what do we do about issuing it? The way it works is pretty much. Many of you will probably recognize that this is a classic sorting problem in that you can sort as long as you have good amounts of memory, you can sort anything, right? But the problem is that usually you have a lot more data than you have memory to sort with it. So because this is essentially a metadata problem, you're trying to cache metadata instead of RAM in order to do the sorting thing. So we track all the queues, and we do understand how much memory they take up. And we try to limit it to a reasonable value, although it's tunable. By default, we limit it to 5% of your physical memory. And if the queues grow just too large, we'll start to issue your largest extents at the front of the queue. And while issuing the ZIO reads, we'll actually pause the scanner part, because the scanner is essentially doing random read I/O, and it really impacts if you're trying to do sequential reads. So basically, that's how we, again, contract the queues, and we try to hover around the 5% physical memory target. Obviously, the more memory you have, the better it works, or the more memory you dedicate to the thing, the better it works. And I'll show that in a couple of benchmarks in a moment. Now, one thing that this really impacts on is the ability to resume after reboot, or you have a machine crash and you want to resume your Resilver or scrub. So what do? This kind of design, this kind of out of order thing, really tends to mess with the old way the ZFS stored the progression records, essentially, on disk. And for scrub, it's really not that big of a problem. But if you miss some transactions from your from your Resilver, that's going to be a bit of a problem. We do it by essentially, in certain periodic intervals, we by default have it set to about once an hour, but it's tunable. We basically just pause the scanner, we stop the whole thing, and we tell it just go through all the ZIOs in sequence and just issue them all, clear out the entire queues. This will take a couple of minutes, but the point is that after you have completely emptied out the queue, and basically what's a simple elevator algorithm, you will at that point have completely consistent state between what the scanner thinks has passed and what the readers have actually issued. And then we can update the DSL scan phys-t structure on disk, and you'll be able to resume from this point on forward. And then we again restart the scanner and keep going, filling up the queues and issuing ZIOs out of sequence, ZIOs reordered and as is necessary. The point is that scrubs and resilvers typically do take a fair amount of time. So if you lose about an hour's worth of progression, if it's a 12-hour job, it's somewhat of a deal, but it's not that big a deal. If you were to lose all 12 hours, that's big. That's kind of a nasty thing. So that's why we've built in this kind of mechanism to be able to continue. And in the end, it doesn't take that much of a toll on performance. It's maybe 5% of performance loss. And the important thing is it avoids any kind of disk format changes. So this is a complete code change. It doesn't really change anything on the disk. So you could just install it, try it out. If you don't like it, roll back, be happy with it. So in terms of numbers, what are we looking at? So this is a completely synthetic test. The best kind of, or I guess worst kind of situation you could look at. So this is basically a 5-drive RAID Z running on 2.5-inch, 10K RPM, 300 gig drives, and it's filled up. And I've basically thrashed it completely with VDBench. It's randomized to the point where the regular stock Resilver was running at about 8 megabytes a second. Yeah, it would take about a day and a half to complete. With this improvement, and the queue size parameter that you see here is basically the value that I've limited the queue to grow to a maximum of 262 megabytes. The reason why that's that kind of a weird number is because the machine I was testing it on had 256 gigs of RAM, so I just set it to 1%, or actually 0.1%. So on this kind of machine, it got an improvement of about 1,600% of performance. Yeah, realistically, this is sort of the worst case scenario. The database guys are probably smiling because this is pretty much what their data sets look like. They're completely randomized. Everybody else is probably going to be a little bit closer to this kind of a number. This is a general purpose file store server that we have at Nexenta, about 26 terabytes of data running on 10 8-terabyte drives. And the regular Resilver takes about 2 days. Or scrub, actually, in this case. It's easier to test scrub than Resilver because you don't have to take drives out. But yeah, this pretty much was done to test what the queue size parameter affects. So if you set it on a 26 terabyte drive, I think the general recommendation, by the way, in terms of memory to data storage, I think we recommend about 0.1%. So per terabyte of storage, we recommend about a gig of RAM. So this thing had about 26 terabytes of data, only took at 1.3 gigs of RAM. It was still 3.4 times faster than stock. If you give it basically 5 times the amount of memory, it'll complete a little bit faster, about an hour faster. But basically this was to test the effects of how much memory you can throw at the thing. Pretty much the finding here is that if you give it just a little bit of memory and if you let it do at least a little bit of reordering, you'll get massive performance gains, at least on spinning Rust. And the final test I have here for you is a test on SSDs. Theoretically, if you work you sit down at the table and think like, does this actually improve SSD performance? The answer would be no. But apparently there is a little bit of a gain here. This was tested on, I keep forgetting, the Optimus SSDs, the SAS SSDs, threw 6 of them in there, put on some data, randomized it, and SSDs generally do take a lot better to randomize crap being stored on them, but still, if you reorder their reads in sequence and give them a little bit of leeway here, you still get a little bit of a performance win, even though it's not quite that much. So yeah, that's pretty much it. If you have any questions or Rotten Tomatoes, feel free to fling them my way. Sure. Yep. Yes, the locking protocol is as soon as you want to touch one of them, you got to touch all of them because. Yes. No, this is all protected by a single lock. This is one data structure. Yeah, the one queue is always locked in one piece because as you can see here on the modification, as soon as you add a ZIO, you got to modify the middle part, and then you got to modify the top part. So all that happens in one step.
So it's one line.
It's one lock.
This is amazing.
Yeah, this kind of a win is pretty amazing. I agree.
Actually, I have a question about this, like what this workflow looks like. So, because you're like you're totally randomizing as much as possible.
Yeah.
How much like continuity? How much continuity were you able to get in those reads? Like, were you able to measure like we took the totally Swiss cheese and then it turned into like completely sequential reads, or was it like half sequential, or?
So the question is, how badly trashed was this data, and how untrashed did we get it? Yeah, this was completely trashed. I think I've let VDBench. This is 32K block size, and I think I let VDBench run a 100% random right on this for about a day and a half. So it's completely gonzo. And the critical part here is that the reordering part does not do it all in one go. It basically tries to do as good a job it can with reordering reads until it hits the memory cap. And then it'll sort of, okay, well, we just got to pick the best target. And it just clears out one of the very largest ones until it gets about 50 megabytes underneath the limit, and then again grows and basically keeps that around. Now, the nature of this beast is that such that as you progress further down, as you get basically to the end of the pool with the scanner, at that point you got to start again grabbing the lower value target ones that are shorter. So the final push to get the thing finalized is going to be a lot slower than the average up until that point. So this took about 2 hours. The main maybe 95% of the data volume is going to be done in about an hour and a half. And the remaining 5% is just the really scramble around bits that you're going to be then elevatoring through once at the end. This is going to be taking about a half hour. So in the end, this is the final average that you're seeing here. The initial thing when you first run it, and then it hits the queue size and it starts issuing, you're just going to be all smiles because it'll run at pretty much drive speed. But that's only because you've just picked out the largest contiguous chunks that you can find, and you'll start issuing those first. Sure.
On a little bit different topic. So you're doing this like checkpointing every hour?
Yeah, roughly.
Does that mean that you are not waiting for those IOs to complete seeking context? And does that mean that we aren't taking up like a big time slice of seeking context to do the scrubbing?
So the question is whether, if I understood you right.
Can we get those IOs going when we're not in seeking context, or is it still only within the
Yeah.
time slice?
So the question is whether the IOs are issued out of or inside of syncing context. They're issued out of syncing context. So the way that it works, normally ZFS Resilver and Scrub, they issue IO only inside of syncing context, and they only scan ahead in syncing context. The way this works is once we hit the memory cap or we hit the time limit for basically a checkpoint, that's when we set a little flag. And whenever we get to the Scrub scanner, inside of syncing context, we look at, well, just it's checkpointing at this point, let's just move on. And then there's another thread that on the background is just chugging along as fast as it can to empty out the queue.
Awesome.
Thumbs up from Matt Aarons. Sure, George. Per leaf VDEV would the question is why the queuing is implemented in top level VDEVs and not in leaf VDEVs. Per leaf VDEV, the problem is the reason why it's in top level VDEV is because that's where your sequential your ordering of data becomes important on disk. Even a RAID Z, which seemingly seems relatively scrambled around, even if you have like contiguous pieces. When you have contiguous blocks on a RAID Z VDEV, a top-level VDEV, it'll still break apart in sequence onto the individual constituent drives. So that's why it was put there. Changing the queuing strategy at the leaf, I'm not sure it'd be easy to do there.
Yeah.
And the trick is that even in a RAID Z, when you have or three contiguous blocks, when you take, for example, for the first drive only in a RAID Z, when you take basically the first portion of each stripe, they'll still be in sequence. So the sequentiality does not break in a RAID Z between leaf and top level.
So then follow-on question. Do you do anything with the VDEV?
No.
Or is it just done, like, do you do any kind of aggregation at that point?
No, we don't do anything on leaf VDEVs.
So really, the VDEV tuning for scrubbing could be removed.
I suppose so, yes. Yep.
I have two questions. The first one is, you were saying that you allow small gaps in the circuit extents or
Yes.
scan sites. How do you determine, like, what size are those gaps allowed, and was that, like, you did careful analysis, or is it just determinable?
So the question is how large are those gaps and whether it was determined through some super complicated process or was just a magic number that we pulled out of where the sun don't shine. It's pretty much a straight up my sleeve number. It's tunable, so it's not hard coded in the code. I've tested out a number of values and on a number of pools, but basically it's tunable at this point. We might fix it if we determine that there's really no reason for it to be tunable, but I don't really see a need to remove that tunability. I got to take a question for up there somewhere.
Following that, there's a similar gap calculation at the leaf level. So you may want to look to see if.
Yeah, I know.
Two similar values. There are two similar values.
Okay, good.
And then I had a second question. This
Oh,
is awesome.
sure.
When can I have it?
As soon as I fix one particular bug in it, but no, it's pretty much feature complete. The only thing that I got to do is there's a little bit of a data corruption bug that where if you try and interrupt a Resilver and then boot to an old machine, it could just cook the pool. But but it's really just about finishing up one of these things, and the bulk of the algorithm is done, and we could just go over it tomorrow in the hackathon if you want to. Anybody willing to sacrifice a pool to the gods of the improved Resilver change is just come talk to me. Sure.
I have two quick questions. First one is, how does this compare to line rate of just using string switches, like sequentially? And second question would be, have you tried to measure the performance while still issuing reads and writes to your pool?
Right. So the questions are: how does it affect? How does it compare to just sequential reading, and how does it affect? How is this thing affected by other I/O happening on the pool? The question of how much it compares to line rate on a drive is pretty much a question of how much memory you can throw at it. If you have a very large data set and you give it a little bit of memory to implement the queues, basically, then we cannot do as good a job of reordering the ZIOs, because you're just going to have a whole bunch of extents, very large extents with lots of holes in them. So obviously you're still going to get some skippage. Then the performance is going to be lower. It'll still be pretty close. It'll be best if you could get it like just unlimited amounts of memory. So you have like a 2 terabyte drive and you just let it have like 20 gigs of RAM. You'll basically cache all the metadata on the pool, and all of your reading is going to be at 0% progress, and your scanner is going to hit 100%, and then you'll start issuing everything in sequence. Then you're pretty much going to get as close to line rate as you can, given any fragmentation on the meta slabs. The second question, what was the second question about again? Right, if you still do I/O to the pool, how much does it affect it? It affects it obviously in a fairly negative manner, in the same way it would be affecting regular scrub. We issue the ZIOs in exactly the same priority and queuing status as regular scrub. So it's more of a question of how much does other I/O happening on the pool affect scrub in general. It affects it to the point where you allow how much you allow it, basically, and how you set up your priorities. At this point, scrub is fairly heftily affected because scrub is low priority. Resilvers are in a much higher priority. But still, I mean, it is going to suffer. You're going to have 2 concurrent workloads. It's not going to be maybe, I don't know, drop down to 5%, but you're going to get a drop of, I don't know, maybe 50% because of other IOs taking priority. Any questions? Sure.
I mean, it's kind of a restatement, just looking at the flip side of the same coin, but I was thinking, looking at this, it looks to me like, my concern is more along the lines of, how does the scrub or resilver affect the rest of the pool? And it looks like, except for that last little bit at the end you're talking about, that sucks just as always did, you'll be requiring a lot fewer IOPS to do the job for most of the time.
Yes, that's the whole. Yeah. So the question is, if this is going to be requiring less IOPS than doing it conventionally up to this point, yes, it'll require a lot less IOPS. It'll still do the same volume, but it'll just do it in another sequence, preferably completely in sequence. That'd be best. Sure. Yeah.
So, could this be extended to balance
Uh,
bots, right? And then it's gonna nicely consecutive or
yeah. The question is whether this could be used to rebalance data, I guess, across VDEV members. I was waiting for when this year the obvious BP rewrite question is going to come up. No, it cannot be used because Scrub does not. Maybe people imagine that Scrub or Resilver, when it discovers a bad block, it'll just reallocate it somewhere. It doesn't. It rewrites it in place. We cannot move data around.
sure, it's found the blocks, sequence them,
Yes,
right?
but
Now a good time to rewrite them.
but keep in mind that, as I said in the initial part of the talk, we don't look at the structure of the data inside. So I don't know if what I'm looking at is a bunch of block pointers or is just your Shakespearean novel. So I cannot move it around. And if I try to move it around, I might break checksum, or I might break block pointers that are in a completely different object pointing to this one. So that's why we wouldn't want to do that. It's BP rewrite essentially re-implemented. Yep.
Just so that I'm kind of sure of how it works. So other than this one checkpoint thing that's going to happen every hour,
Yep.
if you're going to issue and then it's a small one and it's not really connected to anything nearby, is it just going to sit in the queue for like a whole hour?
Yes. So the question is, aside from checkpointing, is the read going to sit in the queue? Yes, it is. But you have to understand that the read is kind of a special read. It's not a read from user space. It's a read from only the scrub part.
The only reason I'm wondering is I'm assuming this is going to be glorified against most versions or against the OpenVFS in project. In Linux, like it'll just print stack traces all over the place because the thread will time out. But that's
The question is whether it's going to affect Linux. No, it's not, because the thread's not going to time out. You're not pausing any threads. The way it works is essentially there are two threads. Well, actually, there's one scanner thread. The scanner part is actually not a thread in itself. It's just done as part of the SPA sync in syncing context. And the read threads are all individual threads per top-level VDEV. And they just sit in a CV wait and a CV timed wait. And once they have enough data to be either kicked off, either consume the top-level most extent or start everything elevating through everything, then that's when they'll get woken up. So you're not gonna. There's no blockage, no obvious blockage, at least not that I'm aware. So as long as Linux has CV timed when implemented right, you should be good. Yep, Paul.
So you said that once the queues get up to, by default, 5%, you start issuing some of the largest segments.
Yes.
Until you drop back below. How low? Do you try to drop like down to 4% or just like below 5%?
The question is how much droppage is there once we hit the memory cap, whether we drop a full percentage point or just a little bit. We try to keep it as little as possible, so we will try to drop by maybe 10 or 20 megabytes under the limit. We don't want to be switching over from scanning to reading too often, but as long as you do it like every couple of seconds, it doesn't really matter. Yep, Matt?
How do you do progress reporting here? Because like there's different progress rates of
Right.
thread versus
Yes.
thread and versus what's
So the question is how do we progress report the thing? There's a new value. So the way that current progress reports work, if I remember right, is you get a scan t in your zpool configuration from the kernel. We put in another value in there, which is basically read progress, and kept the old one as the scan progress. And it's also a modification of ZPL status of the printout, and you'll get 2 lines on there. Well, it's one line. I don't remember exactly which one. You'll get basically 2 printouts there. One of them is scanning progress, and the other one is reading progress. So you can easily, and the time estimated is based on the reading progress. That's been changed so that you don't get like bogus values, like I'm remaining 0 minutes, 0 second, and it's still not done. So,
I guess kind of a follow-up to that is, are you storing state information in a temporary area that's affected by the fluid environment?
no. Question is, where do we store basically persistent state of this? How do we keep track, and what do we resume? That's already being done by regular ZPL scanning and scrubbing and resilvering. It's part of a structure called DSL scan FIST, and per sync and context, you basically issue this this kind of, you basically write out this record that'll tell you I've scrubbed or resilvered up to this TXG and then that TXG and that TXG. It's basically keeping that kind of progress. And it does a little bit more. It does TXG and object set number and object number and offset within the object and so forth. And once it gets around back to the next syncing context, it'll pick that up again, look at where it was, and keep going from there. So it does it, it sort of stops and starts. This only changes it insofar as we don't write out the DSL scan FIST every transaction group number, but only once we are done with the checkpoint and we have cleared out all the queues, so we are certain that we've gotten up to this very point. That's when we issue the write in syncing context, and then we keep going with the scanner. Yep.
Did you mention that you added another integer to the scan object?
No, not to the scan persistence objects.
Oh, okay. I'm sorry. I was going to say that would imply a change on this format.
Yep, it doesn't, yeah, so we're not changing on this format. Yeah.
I just want to make sure I understand. I know I'm going to have to answer this question later. Why we can't reorder the data while we're scrubbing or resilvering. What I'm understanding is it's because if the block contained pointers, you might actually have to then chase it potentially all the way back up to the Cooper block to actually be able to reorder it, correct?
Yes, that's basically, you're describing the common problem called block pointer rewriting, is that block pointers themselves are not, the checksums to block pointers are not in the block pointer, in the blocks, but in the pointers to them. So if you rewrite anything that contains a block pointer, I gotta finish up, this is the last question. Whenever you rewrite the block, that means you've changed the checksum, but there's a myriad of places that can still refer to that. So you gotta go all these places, modify those, and then there's other places referring to those places, and you gotta basically chase the file system tree all the way back in the wrong direction.
Including all the snapshots.
Yeah.
I mean, that's the real hard thing about the computer, right? Is you have the same block pointer is in a whole bunch of different snapshots, and you have to remember to go change it in all those snapshots as well.
So pretty much for any rewriting of a block that's already committed, you would have to then pretty much scan the entire file system and find all the occurrences that have been referring to it and rewrite those, and then go back again. It's basically an exponential kind of problem, and makes file system people's heads explode. Okay, thanks.